Hello and welcome to this video lecture series on microprocessor and microcontroller. And from this lecture onwards, we are going to start this important concept of interfacing, right? And we are going to study this interfacing in context of 8086 microprocessor. So, first of all, there are two things that we need to address before beginning this lecture. Why are we studying interfacing in context of 8086 only? We could have also studied this in context of 8085, but the thing there is that 8085 is fairly simple microprocessor as compared to 8086, and 8086 has a separation of even and odd memory banks. So some of the concepts of external memory interfacing are little more complicated as compared to 8085. So if you study them here, it will be easy for you to study them for 8085 on your own. So that's why we are using this 8086 microprocessor system, right? The second thing that we need to address here is that what are we going to do with this interfacing thing? So the thing is, microprocessor 8086 in itself is just like brain, right? It has got capability to do things, but it won't be able to do things if we do not have peripherals which are interfaced to itself, right? So from microprocessor, we need to create a microcomputer system. A microcomputer system is a combination of a microprocessor together with its peripherals. So that's what we are going to do. We have spent a fairly good time in studying 8086, its fundamentals, and now it is a time to create a microcomputer system. A microcomputer system will have this processor. It will also have its peripherals like keyboard. It will have a monitor, not the monitor that we see today, but maybe a 7-segment display, and various other things will be interfaced to it. So that's what we are going to see. So this is the 21st video lecture in the complete series and the first video lecture for interfacing, right? And the topic of today's video is interfacing external memory to 8086 as well as interfacing input-output devices or input-output ports to 8086. So that's what we are going to do. But before beginning this lecture, let me just show you this syllabus that we have complete up till now. So you can see here we have completed 8085 first in great details. However, we didn't bring this interfacing thing there because I saved it for 8086. So we have dedicated 10 lectures for 8086. So we started with architecture, where we studied the hardware construction of 8083, the internal hardware construction and what is the role of each and every element there. Then we studied the pin diagram. I mean, if you purchase the 8086 microprocessor, we will be able to access it through its pins. So we studied the detail of every pin, and then we saw the programming model. In programming model, we saw what portions of microprocessor are accessible to us as programmers. So that's what we saw there. And we dedicated then the next 3 lectures for making simple programs in 8086. So there we studied how to deal with the externally interfaced memory, how to do interrupts. Interrupts we dedicated a separate lecture where we studied the interrupt structure. And we made some simple programs on how to deal with stack, how to deal with memory, how to do some simple input outputs. So that's what we covered there. Then we studied the 2 modes, maximum mode and minimum mode of operation for 8086. So it might be the case that 8086 is operating alone in the system. So that's what we mean by minimum mode, alone microprocessor. If it is there, then it is minimum mode of operation. And in maximum mode, 8086 operates with other processors in the system, which might be another 8086 or another math coprocessor or something else, right? So that's what we studied in these 2 lectures. Then after we started with addressing modes and instruction set part 1, where we saw the addressing modes primarily, how many addressing modes are there. And then we started studying the instruction set. So we have dedicated 1 lecture to that, although we haven't been able to cover all the instructions there because the list of instruction set of 8086 is fairly long as compared to 8085. So we will study them in the laboratory sessions because anyway we are going to make programs there. So instruction sets are best studied by practicing them. So we are not going to dedicate any further lectures for studying instruction set. We will cover them when we will make programs in laboratory sessions, right? So after that, we studied the memory organization of 8086 in the last lecture, and that's what we need to remember for today's lecture also, because 8086 memory is different from 8085 memory on various grounds. First of all, the memory is segmented. So you can make 4 logical segments into your completely externally interfaced memory, which is of 1 megabyte size. Other than that, the hardware implementation of this memory is such that you need to have an odd bank and an even bank, right? And we studied that on the last lecture. So let me just show you the slides and let us quickly revise that, because that will be used in this lecture also. So we took a pilot example where we said that if we had a memory which had only 16 locations, and each location is of 1 byte. So it could be either a single chip of 16 locations, or it could be broken into 2 chips of 8 locations each, and that is called, one of them as odd bank and other as even bank, right? And since 8086 is a 16-bit microprocessor, so you have a data bus of 16 bits, and that data bus, its lower order byte is connected to this even bank and higher order byte is connected to this odd bank, right? But if you have only single memory chip, you cannot connect the entire data bus into the 8 bits of one location, because ultimately out of this memory chip you will have 8 wires coming out, or 8 connections coming out to interface the data bus, which will be same for this. But then we have got a data bus of 16 bits. So you need an additional hardware to interface this kind of memory to your system. However, here, since you have separated it in 2 parts, you can just put your complete data bus into these 2 chips at once. And that is advantageous because if both of these memory banks are activated, which will happen when A0 is 0, so this is an active low signal, so this will activate this even bank, and if this BHE bar is also 0, so this is also active low signal, this will activate this particular bank. So in one machine cycle only, the complete data of 16 bits can be transferred to both of these chips. So that was the whole sole aim of dividing the memory into odd and even banks. And odd and even banks are not named randomly, since if you see these yellow ones, if you see these yellow addresses, they all end in 0. So whatever numbers end in 0, if you convert them to decimal system, they will be all even. So you can see that representation here, they are all even numbers. That is why A0 is used as a select line. And regarding the address lines, if you see the address lines here, in this original chip, you had 4 address lines because you had 16 locations. So 2 raised to the power of 4 is 16. However, in this, you can only have 3 address lines. So what we have done is we have connected A1, A2 and A3. This A1, A2 and A3 here, and you can see that A0 is used as a chip select signal for this particular even bank. And for odd bank, we have got BHE bar. So we need to keep this in mind to be able to understand today's lecture. So let me just come to today's lecture. And in today's lecture, as we have already said, that we are going to study the interfacing of memory and input-output devices, right? So let me just quickly begin by pointing out some important points about this interfacing thing. So first of all, peripherals, they are of 2 types. I have written several points here. We will discuss these points one by one, and we will see the relevant diagrams also. So let's discuss these first 2 points first. Peripherals are of 2 types. First is general purpose peripheral and second is dedicated peripherals. General purpose peripherals mean that you need to have a memory with a microprocessor, because if you do not have memory, the microprocessor simply won't work, because your programs are written in the externally interfaced memory only. They are not written inside the internal registers of the microprocessor. So this is a general purpose peripheral. You need to have this. Similarly, display is also essential. If you do not have a mechanism of seeing what's going on inside microprocessor in terms of obtaining your results, etc., so you do not have very much use of that microprocessor, right? And similarly, you need to have a keyboard to be able to interact with that microprocessor. We need to have keyboard, and also you will need to have some input-output ports. Because if you have some USB device, or in those days when these microprocessors were designed, if you have some specialized chips which contain some data, so you need to take data from those chips. For that, you need to have some input-output ports. So these are general purpose peripherals. They need to be there. These are the basic minimum peripherals that should be there in the microprocessor so that it should be able to perform. Then there are some dedicated peripherals, right? Some dedicated peripherals are there, like this PIC, DMA, and CRT controller, right? Programmable interrupt controller, direct memory access, and this cathode ray tube CRT controller, right? So these dedicated peripherals are there. We will discuss more about them when we will study the interfacing of these things with this microprocessor. So there are two types of peripherals. So now let's talk something about this semiconductor memory, right? Semiconductor memory is of two types: RAM, which is again of two types, static RAM and dynamic RAM. Similarly, you have ROM. You're already aware of what RAM is, random access memory, and ROM, which is read-only memory. So ROM usually contains some system critical programs which are used to run the system. So ROM is there, and you have RAM, which is random access memory, and it is used to accelerate your programs. I mean, it is used to improve the speed in your computers as you know them now, right? So RAM is of two types: static RAM and dynamic RAM. So static RAM is usually very costly and dynamic RAM is less costly, right? It is actually very cheap. So this static RAM actually acts as the cache memory of the system, right? So dynamic RAM is in actual sense the RAM that we put in our computers today, right? If you want to improve the speed of system, you go to a shop and you buy some RAM and put in the slot for the RAM on your motherboard. So that's what we mean by a dynamic RAM. And static RAM usually is a cache memory which is usually present with the computer, and it is actually very, very fast. There are some differences in construction of static and dynamic RAM which makes them different, which we are also going to discuss in this particular lecture. ROM similarly could be either static or dynamic, but usually ROM is considered as static because we do not need ROM to be slow. So that's why I haven't written static ROM and dynamic ROM. So if it is ROM, it is meant to be static only, right? Then usually the memory is represented in this way. They will usually write this 4K cross 8. What will it mean? It will simply mean that you have 4K locations of 8-bit each. Or an alternate way of writing this is you can simply write 4K bytes or 4 KB memory is required. Right? So 4 kilo locations are there. You understand what kilo is. Kilo is 2 raised to the power of 10 in binary system, which is 1024. So you will have 4 into 1024 locations, and each location is of 1 byte. So this is what we mean by representation of memory. So whenever someone says I need to have a 4K cross 8 memory, they mean that they need to have a 4 kilobyte of memory. Right? So another important point of interfacing the externally interfaced memory to your microprocessor is this. First of all, lower order address lines are used as address lines, right? So if you are interfacing less memory, I mean the externally interfaced memory can be of 1 megabytes. You do not usually use the complete 1 megabyte memory location for addresses. You have some less memory. You have purchased only few chips, and you believe that your program will be able to run in that. So why purchase a complete big chip? So on that end, if it is the case, then a good practice is that lower order address lines are used as address lines. So we have got 20 address lines here because the address bus is of 20 bits. And if you want to use full capacity of the address bus, then you will have complete 1 megabyte memory. But if you have any less memory, then it is preferred that you should begin from the starting addresses, means 5 times 0, then 00001, 00002, and so on, right? So it is preferred that you begin from the numerical order of memory only. You should interface your memory in that order. Or if you interface it from some other location, it should be in continuous fashion. I mean, it should not be the case that you have one chip starting from 00000 and ending at suppose 64 kilobytes after that, and after that you leave some gap, and then after you start your memory locations. Although that is technically not impossible, that is done in some of the cases, but it is a good practice to keep your memory in continuous locations. Then higher order address lines which are left. I mean, if you are using some less memory, then obviously less address lines will be used to address that complete memory. So whatever lines are left, whatever address lines are left, those are higher order address lines, and they are used for generation of chip select signal. So this will become clear to us when we will see an example in this lecture only in a short while. And this point I have already discussed. It is desired to use continuous locations for memory chip interfacing, right? And I would also like to keep one more point here, that when a microprocessor is reset through external pin, then the control is transferred to FF0 in hexadecimal, right? So when a microprocessor is reset through external pin, then the control is transferred to FF0H. Mind you, I have written these 5 hexadecimal digits. I mean the actual physical address here, right? So this is also one of the important points to note, that when a microprocessor is reset through external pin, that is in the pin diagram of microprocessor, there is a reset pin. Then the control is transferred to FF0H. And whenever a microprocessor is reset, it will just start executing the programs which are written in its ROM. So it's a good practice to keep your ROM interfaced to this particular address. I mean, your ROM should include this address, so that when a microprocessor is reset, it will start reading the instructions after that to be able to start the system, right? So this is also one of the important points. Now let us see an example, and let us try to interface a static RAM using this 8086, right? So the problem here is interface two 4K cross 8 EPROMs, that means ROM is there, and two 4K cross 8 RAM chips with 8086. So this is the problem that we are going to address now, and you can see that on the screen I have written a lot of material. There are a lot of diagrams. Don't worry, you will be able to understand them all. The only point is, if you are firm in the concepts that we have developed for 8086, this will sound very easy to you. So we have two 4K cross 8 EPROMs, that means one for even bank and another for odd bank, and we have 4K cross 8 RAM chips. So these are also 2 in number. One will be for even bank and one will be for odd bank, and we want to interface it with 8086. Now this usually happens in 8086. You buy RAM in pair or you buy ROM in pair because you need to have an odd bank and an even bank, right? So that's what you usually do here. And in 8085, you can only buy a single chip and interface it to the microprocessor, right? So now let's begin some discussion about this. If you see this size of the memory, 4K cross 8, 4K locations are there for ROM, right? And 2 such chips are there. So you have a total of 8K locations. 8K locations will be there. And K means 2 raised to the power of 10. And obviously 8 means 2 raised to the power of 3. So 2 raised to the power of 3 into 2 raised to the power of 10 will become 2 raised to the power of 13. So 8K locations will require 13 address pins or 13 address lines. So the lower order 13 address lines will be used to address these 2 EPROMs of size 4K cross 8 each, right? So we have 8K cross 8 a total memory. We have a total memory of 8K cross 8 because we have got 2 such chips, and it will be using address lines from A0 to A12. So that is why we have complete 13 address lines here. So that is the case here, right? And similarly, if you see here, you have got 4K cross 8 RAM chips. So these RAM chips are also of the same size. So you have 2 such, so you will have 8K cross 8 of them. So this 8 means 2 raised to the power of 3 and this means 2 raised to the power of 10. So ultimately 2 raised to the power of 13 address lines will be required. So address lines from A0 to A12 will be used there, right? So after this, now what we need to do? We need to just interface these chips to the 8086 microprocessor. Now, can we keep it anywhere? I mean, you have got two chips and you have got address bus. The address bus, it has a special pins on this pin diagram of 8086. So can you just take wires and connect them to these two EPROMs in just any random order? No. There has to be some logic and reason behind that. So for ROM, as I have already discussed, that whenever the external reset pin is set, the address automatically goes to FFFF0, that is 4 times F and 0 in hexadecimal. So that location should be included in ROM. And you can see that FFFF0 is an address which will come at the last portion of the 1 megabyte location. Complete 1 megabyte addresses that can be there in 8086. So that address comes near last locations. So this ROM should be interfaced near the last locations, right? And whatever space it will consume, we need to use the space prior to that for this particular RAM chip, right? So this RAM and ROM will be interfaced in continuous fashion, and since EPROM is bound to have the address of FFFF0H, so that is why in the address range we will try to interface this EPROM at the end, and before that we will stack up this particular thing. So that's what we are going to do. Now, so if this 8K locations of this EPROM are used and we are trying to interface it at the end, so the last address will be definitely FFFFH. This is the last address, 5 times F in 1 megabyte location, right? Now, if you want to go to locations 8K before that, because you have two such chips, so you will be subtracting 8K from that, right? And 8K, if you see, it is 2 raised to the power of 13. So here I have written the binary representation of that number. So 13 bits. You start from bit number 0 and you go to bit number 12. So these many bits will be 1, rest everything will be 0. And if you convert this into the hexadecimal number, so these first 4 bits, they are all 0, so this is 0. These second are 0001, so this is 1. Similarly, this is F, F and F, right? So the hexadecimal number for 8K is 01FFF. So why are we requiring this 8K? Because we have two 4K chips. So we have 8K locations, and since we are interfacing those 8K locations in the end, so the last location will be FFFFH, and we need to subtract 8K, that is 01FFF from that to be able to obtain the starting address of these two EPROMs, right? So if you subtract 01FFF, so you can see that last three Fs will become 0, and F minus 1 will become E, and F minus 0 will become F. So you got this FE000. So from FE000H to FFFFH, you have addresses for ROM, right? Two ROM chips will be interfaced there. And we said that we need to have continuous memory locations. So that is why we will now try to interface the remaining 8K locations for two 4K chip of RAMs to be stacked over this, right? So one location prior to that, FE000, is FDFFH, because in FDFFH, if you add 1, it becomes FE000. So this is the location which is now vacant. This is one location prior to the location from where your ROM is starting, right? So you see here that you again want to have this 8K locations prior to that. So 01FFF is needed to be subtracted from that. So if you subtract this number again from this complete thing FD000H, you will get FC000H. So this is the starting address of your RAM chip, and this is the ending address of your RAM chip. So in between these two addresses, you will have two RAM chips. Similarly, in between these two addresses, you will have two ROM chips, right? So that's what we have done here. And by mistake, I have written address lines till 11th. However, it should go up to 12th. So because we have already discussed that 13 address lines will be required. So from A0 to A12, this address lines should extend up till here, and the remaining bits, that is from A13 to A19, will be used for chip select logic, right? So these are the two locations for two EPROMs. These are the two locations for two static RAMs, right? So these are faster RAMs. For dynamic RAMs, there is a different procedure which we are going to discuss soon. So this is for static RAMs, and the offset for both of them comes out to be the same, 0, 1 FFFH, means the total number of locations that it will consume, because you have got the same sized chips. So this is what is our plan, right? So after having understood this chart, now what we will do is, we have got these ROM chips, right? Do not look at anything else. Just look at these 4 chips. 2 of them are ROMs and 2 of them are RAMs, right? So you can see that in the address lines, you will have the connections from A0 to A11, right? A0 to A11 here. This is the internal chip of ROM. Now you will wonder why I have this A0 to A12, I have said that A0 to A12 should be the number of address lines that will be used. But here, since this memory chip contains 4K locations, and 4K locations, it will only mean this 4 is 2 raised to the power of 2, and this is 2 raised to the power of 10. So only 12 address lines will be used for one ROM chip. Combinedly, for 2 ROM chips, you will be requiring 13 address lines. So now how to accommodate this, right? I said that 13 address lines will be required, and that is why we will require A0 to A12, that is these all locations. But if you see individual chip, then only 12 address lines are required. So this is fair. This is okay. Why is this okay? Now let me tell you the reason for this. Again, let us come back to what we have discussed in the previous lecture. If you see that if in the pilot example that we have discussed, if you have a single chip versus you have 2 chips. So in 2 chips, one less number of address line is required. You do not require 4 address lines here. Although for the original chip you require 4 address lines. However, if you break it into 2 parts, only 3 address lines will be required, and one bit, that is A0, will be used as the chip select for this particular signal. Right. So that's what we are going to do here also. If you again see this particular diagram, here address lines from A0 to A11 are there, and here also in this ROM chip, address lines A0 to A11 are there. So these are not the address lines of microprocessor. The notation that you see here, A1 to A12, these are the address lines which are coming from the microprocessor, and they have been interfaced to this ROM and RAM chips, whose address lines are numbered as A0 to A11, A0 to A11, right? So this A1 to A12 are coming from the microprocessor, and A0 is simply A0 is not taken here because we have seen it in the pilot example that it will be used for generating the chip select logic, for selecting the even band. However, the chip select logic here is little more complicated, so we are coming to that, but this should be first of all clearly understood. So these are 2 ROMs, and this is how address lines will be connected. On the same logic, since RAM has got the exact same size, this A1 to A12 lines of the microprocessor will be connected to the A0 to A11 lines of these 2 RAM chips. So now we have connected the address lines to our RAM and ROM chips such that we want to implement this complete table, right? So these RAM chips have been connected. Now the data lines, that is D7, data lines, they are of course of 16 bits in microprocessor. So you can see that the lower order byte is connected to this even RAM and higher order byte is connected to odd ROM, right? Similarly for RAM also, you have connected the data lines here. So these comes from microprocessor only. So we have done this thing that we have got 4 chips, their sizes are specified, we have connected the address lines, we have connected the data lines. The next and very important thing is to be able to implement this table. That is, we should be able to generate a chip select signal for these particular lines, when which thing should be active, right? So that's the next thing that we are going to discuss. How to generate the chip select signals. So from A0 to A12, you can see that these lines are busy for address. From this chip select logic, you have pins from A13 to A19, right? So neglect this particular portion. Neglect this particular portion here. This was used for calculating these addresses. Now focus on this particular portion. In this, you see that lines number, if you see A12 is used for address. After that, if you see from A14 to A19, right, A14 to A19, whether it is ROM or ROM, it always remains 1. It always remains 1, right? So this is one fact. A14 to A19, whether it is EPROM or SRAM, it always remains 1, right? So A14 to A19 is clear to us. Now A13, it is 1 for ROM chips and it is 0 for RAM chips. So we have these two facts. First is A14 to A19, it remains 1, whether it is a RAM or a ROM. And this A13 is 1 for a ROM and it is 0 for a RAM. So these are the two facts that we have got, right? Apart from this, we already know that A0 and BHE, how they operate. From the previous lecture, we know that how A0 and BHE operate in activating or deactivating these things, right? So now, what I have done is, to be able to generate the address decoding logic, I have used a 3:8 decoder here. This is a simple 3:8 decoder. The only important point to note about this is it has got active low outputs, right? So these are the three inputs, A0, A1, A2. Do not confuse them with the address bus. These are the notations for this particular IC. So if you and the outputs are active low, so you have outputs from Q0 to Q7, a total of 8 outputs. So whatever input combination will be applied here, right? So suppose if I apply 5, these are all active high pins and the output is active low. So if I apply an input as 5, that is 101, the binary equivalent of 5 is 101. If I apply that here, then the fifth bit will be 0, rest all will be 1. So this is an active low output decoder. So this is the only important point to note about it, right? So in this decoder, I am applying these signals, BHE bar, A0 and A13. So this is BHE bar, A0 and A13, and there will be 8 different combinations which will be generated out of that. So these A0, A1 and A2 are the notation for decoder. So you can see that A0, A1 and A2, these are the decoder inputs, and to these inputs you have plugged in BHE bar, A0 and A13. So this is BHE bar, this is A0 and this is A13. And you now see, you already know how this A0, BHE bar and A13 will operate. A13 is this, it is 1 for ROM and it is 0 for RAM. So let's look at any combination. If this BHE bar is 0, A0 is 0 and A13 is 0. If this BHE bar is 0, that means higher order bank, that is the odd bank, will be enabled, right? Whether it is ROM or RAM, wherever it is attached, the odd bank will be enabled. If this A0 is also 0, that means the even order bank should also be enabled, right? And if this A13 is 0, you can see in this table, A13 is 0, that means the RAM portion of that should be active, right? So we have got here 0, 0, 0. So even and odd address in RAM should be active. And that's what we have also confirmed from our understanding, right? Similarly, you can see this 0, 1, 0. Let's use this combination 0, 1, 0 here, right? So BHE bar is 0, that means odd order bank is activated. A0 is 1, that means the even bank should not be activated, and A13 is 0, that means if A13 is 0, you are using RAM chips. A13 is 0 for RAM chips. So 0, 1, 0, let us see if that is the interpretation. Only odd address in RAM. So that is also true. Only odd address in RAM will be used. So RAM chip will be used and only odd address, that means this particular thing will be activated. So you see here BHE bar, A0 and A13. So these are the signals that you have obtained here. 0, 1, 2, 3, 4, 5, 6, 7. Still, we have not completed our interfacing. We need to generate chip select signals out of them. So first of all, let us look at the chip select of this particular IC, of this particular ROM. 6 and 4 have been ANDed. So 6 means 110 and 4 means 100. So you see here 100 is this even and odd address in ROM, and 6, that is 110, is only odd address in ROM. So if you have ANDed these two. So 6 and 4 have been ANDed, and after ANDing them, you will get something here. Remember that the outputs that you are obtaining from this 0, 1, 2, 3, 4, 5, 6, 7, they have been taken as an input of AND gate. And remember that these are active low outputs. These are active low outputs, right? So if the output corresponding to 6 and 4 is taken, so this is 6 and this is 4. So if these two outputs are ANDed, so then only this chip will be activated. So 6 simply means even and odd address in ROM, and 6 simply means odd address in ROM, and 4 means even and odd address in ROM. So you are talking only about ROMs, and in one case you are talking about even and odd address, in another case you are talking about only odd address in ROM. So these two signals have been ANDed, right? So suppose that 6 signal is active. What do I mean by active? That this 6 signal will be 0 here. This 6 signal will be 0 here. Whatever input is applied here, corresponding to 6, 110 will be applied here. That is, this BHE bar will be 0, 1 will be this value, and A2 will be equal to 1. That is, A13 will be equal to 1. If this combination is applied here, then 6 will be active. If it is active, that means it will be 0. It will be 0. And at that time, obviously, 4 will remain inactive. That is, 4 will be 1, because this is the rule for a decoder. Only one of the inputs should be active. And since this is an active low output decoder, so if this is 0 and this is 1, then in that case, the output of this gate will be 0, right? So if it is 0, then this is an active low chip, because you can see a circle here, this chip will be activated. So this odd bank will be activated, which we want, only odd address in ROM, right? Now see it for 100. If even and odd address in ROM both are to be activated, then these 100 will be active. So when 100 combination will be applied here, fourth output will become activated. That means it will remain 0. So if it is 0, this fourth output will remain 0. So if this is 0, then you can see that this bank will definitely be activated, and you can see that 4 is also applied here. So if it is 0, then obviously the output of AND gate will be 0. So this will be activated. Similarly, you can see it for this logic gate also. You can generate the chip select signals CS3 and CS4 for these AND gates also, right? So this logic is completely written here, and it can be easily understood. So this is how you implement interfacing of externally interfaced memory to this particular thing. Another important thing is, we discussed that bit numbers A14 to A19 will always remain 1. So if this is the case, then only this decoder should be activated. Otherwise, if there is any other combination from A14 to A19, this decoder should be deactivated. So you can see that A14 to A19 have been ANDed here, or rather NAND gate has been used, since these are active low input pins. So and a NOT gate is used because this E3 activator is actually active high. So on that grounds, you have got these things here. So whenever the input combination of these address lines is all ones from A14 to A19, then you can see that this decoder will be activated, right? Otherwise, if there is any other combination, this decoder will not be activated and these memory chips will not be accessed. So this is how static RAM is interfaced. Now, let us quickly have a look at another example of still interfacing a static RAM, right? So this is another example. The difference between previous example and this example is that here you won't be able to interface memory in two consecutive locations. You have to keep some gap between them. So for gap, we are going to discuss what to do. So the difference that you will see here in the final circuit is, instead of using decoder, you have to use dedicated NAND gates here. Instead of using decoder, you have to use dedicated NAND gates. So if you have got continuous locations, then decoder can be used, or if the locations are not continuous, then you have to use separate NAND gates for that. So this is a similar example. The problem here is design an interface between 8086 CPU and two chips of 16K cross 8 EPROM, right? So EPROM has got 16K size, and each location is of 1 byte. So you have got two such chips, so it will be 32K for ROM. And for RAM, you have got 32K cross 8 chips, but they are 2 in number. So it will be 64 because you have got two chips. And the constraint is, select the starting address of EPROM suitably So EPROM, because it is a ROM, so we need to have this FF0H inside EPROM. So we will interface this EPROM at the end of the 1 megabyte addressable space, and the RAM should start at 00008. So this is another constraint. So ROM you have to interface in the end of 1 megabyte addressable space, and RAM you have to put it in the beginning. So obviously there will be a gap, because the 64 kilobytes of this thing and 32 kilobytes of this thing, they do not sum up to 1 megabyte. So that's why there will be some gap. So let us first discuss the chart for this. Since we have to interface ROM in the last, so FF is there. The last location of ROM should be this, and there are two ROM chips. So you have 16 plus 16, that is 32k locations, and 32 means 2 raised to the power of 5. And k means 2 raised to the power of 10. So 2 raised to the power of 15 locations will be used for this particular two ROM combinations, right? So 2 raised to the power of 15, I have written the binary equivalent. You can see it here. So bit number A14 should be 1. And before that, all of them should be 1, because it will make 15 bits 1, and rest everything should be 0 here, right? So the combination would be 07FFF. So 07FFF should be subtracted from FFFF, and you will see that you get F800H. So between these two locations, two chips of EPROMs will be interfaced, right? Now, to be able to interface RAM, you should keep this constraint in mind. 0000H should be the beginning address. So you can see here, you can simply see here that these two chips are there. So 64k locations should be there, and 64k, if you convert it to binary, you will have 16 number of bits which should be equal to 1. So A15 till A15 from A0, you should have ones. So the combination would be 0FFFF. So the starting location of RAM is fixed as 000H, and you add 0FFFH to that. So the last location will be 0FFFH, right? So there you will interface all these things. And another important point to note here is that for the EPROM chip, since 15 address lines were used, so from A0 to A14 address lines will be used. And for RAM, if you see, 16 address lines will be used. So A0 to A15 will be used, right? So there is a difference between address lines that you will combine to the externally interfaced chips for ROM and RAM, because this time they have got different sizes, right? So you have got these 4 chips, as you can see here, 2 ROMs and 2 RAMs. Let's call this pair as even and this pair as odd. And if you talk about ROM, as we have already specified that for ROM, 15 bits of addresses will be used. So you can see that from A0 to A14 has to be used, and this A1 to A14 will be connected from the microprocessor to both of these chips, as per the logic that we have discussed in previous lecture. A0 will be used in this selection of the chip logic. So A1 to A14 have been connected here, and on the similar note for RAM, you have got 16 bits. So A1 to A15 have been connected to this particular thing. And data lines will be uniformly connected to everyone, the lower order byte to the even address and the higher order byte to the odd address. So it has been connected here. And now the next important thing is to be able to provide chip select signals to all of these. So chip select signals logic is designed here. If you want to design the chip select logic for, say, this particular ROM, CS1 bar. So you see this CS1 bar, it comes from BHE bar and this C signal. The C signal is generated from this particular NAND gate, right? So the C signal is an input to this, and C signal comes from this. So let's take a simple example rather than this, where this chain is not there. So let me preferably select this. Okay, so first of all, let us discuss this C signal and C complement signal. Remember that the C and C complement are not the complement of each other, right? The C is a different signal and C complement is a different signal. They are not complement of each other, right? So this notation is little misleading. The author should have written instead of C some other variables. So do not confuse them as the complement of each other, right? So here you can see that A15 to A19 have been NANDed, not ANDed. This is a NAND gate because you can see a bubble here. So they have been NANDed to create this C signal, and A19 to A16 have been used to create this C complement signal. And you can see that this is again this is a NAND gate, but it has got inverted input. So it actually becomes something else, right? So you see here, why have we done this? So if you see this EPROM will require 15 address lines. So from A0 to A14 will be busy in addressing. Rest A15 to A19. A15 to A19, they will all remain 1 for EPROM. So this A15 to A19 have been ANDed. So, right, ANDed, and a NOT gate has been applied, so they are NANDed to generate an active low chip select signal. Similarly, for this static RAM, 16 bits of address will be used. So A0 to A15 will be used, and you see rest of the bits are all 0. That is A16 to A19 are all 0. So A16 to A19 have been put here, and you can see that they have been NOT gates because these are already 0, so they have been made 1, and the NAND gate has been used after that to create an active low chip signal. So this is C complement signal. So this is used for activating this EPROM and SRAM, right? So that's why these C bar signal and C signal are important. Having understood this, you have got 4 chips. So that is why you have got 4 other gates for activation. So if you now talk about this ROM chip, it is, C16 cross 8 ROM, and the activation is CS1. So if you now look at this CS1 signal, this CS1 signal is a combination of BHE bar and this C signal. So C is obviously an activator for this ROM. If you see this A15 to A19, this A15 to A19, they are free. A15 to A19, they are free for this EPROM. So that is why the C signal has been connected there in active low input. And then this BHE bar signal, because this is a higher order ROM, so that is why this chip signal has been generated here. So you can similarly understand all of these things, all of other gates also for being used as activator here. Apart from this activation circuitry, which is constructed from these NAND gates, you also have this memory write signal, memory read signal, which will come from the control bus of the microprocessor. So they are also interfaced here. They will only come to this RAM, not to ROM, because for ROM, ultimately, we are only trying to read data from that. So for RAM, these 2 signals will be there. So the only point of difference from previous example here is that you require these separate NAND gates. Separate hardware is required for decoding of this. Although in the previous example also you required an active low decoder here, right? So that is the case of interfacing these static RAMs to 8086 microprocessor. Now let us talk about dynamic RAM interfacing. Before we talk about dynamic RAM interfacing, let me just make some important points about this dynamic RAM. So this dynamic RAM, it's actually different in construction. Dynamic RAM, it is actually different in construction as compared to this static RAM that we have. In static RAM, it will actually require, it is written here, a typical RAM cell will require 6 transistors, right? If it is a static RAM. While dynamic RAM requires 1 capacitor and 1 transistor. So this static RAM, let me write S here. So SRAM will require 6 transistors. However, DRAM or a dynamic RAM will require only 1 transistor and 1 capacitor. So you can now list the advantages of dynamic RAM. So first of all, this dynamic RAM, whenever it is used, we use several kilobytes to megabytes. And it is not like in the case of this static RAM where we were using byte oriented or nibble based memory. Right? In static RAM, we have seen that every location was only of 1 byte or 1 nibble. So they were used there. However, if you talk about this dynamic RAM, the size is usually very big because cache memory, which is static RAM, is smaller as compared to the dynamic RAM. Dynamic RAM is the actual RAM in the current terminology which we use today. So it is having a bigger size, right? It has got higher packaging density because of this factor number 6.5 that we have just discussed. It has got low cost. Obviously, we do not need to fabricate more transistors. So it has only 1 transistor and 1 capacitor. So low cost, obviously lower power consumption will be there because of this fact again, and because of these facts, it becomes advantageous for us to use dynamic RAM. But it has got certain disadvantages also. The disadvantages of DRAM are this capacitor, it cannot hold charge for a lot much amount of time. Because ultimately, if you fabricate a circuit, on that you cannot fabricate a capacitor directly. You have to use a reverse bias diode, and the capacitance of a reverse bias diode will be used as capacitor there, right? But the problem with a reverse bias diode is that it has got certain leakage current. Because of that leakage current, whatever charge is there on that capacitor, it will be discharged soon. So this capacitor needs to be refreshed again and again. This capacitor needs to be refreshed again and again, so that that whatever charge is stored on there, if a value of 1 is stored on there in terms of logic value, then it should remain 1. The charge should not drop significantly so that we can start treating it as 0. So we need to refresh that capacitor again and again. And this refreshing of capacitor, it requires a separate circuitry, and that is why the operational speed is reduced, as well as additional hardware for refresh mechanism is required, right? So that is why DRAM is disadvantageous for us. So refreshing mechanism is the major point. But again, since DRAM has got these advantages, we will be using DRAM for our purposes, right? Because it is very cheap as compared to SRAM. So refresh cycle now versus memory cycle. Now what happens is, when a DRAM is there, as I told you that since there is a reverse bias diode which is treated as a capacitor, and because of leakage current, the capacitor will simply discharge. So we need to refresh it. Refreshing it means whatever is having a logical value of 1, it should remain 1, right? So that if the charge is discharged, we further need to charge that capacitor by giving it a value 1. So that's what we mean by refresh. So it is actually similar to the memory read and memory write operation. You first read some memory location, it is 1, but the charge level has been dropped beyond a certain value. So we further want to enhance its charge level. So that's what we mean by refresh cycle. So refresh cycle is similar to memory read and memory write cycle, but there are differences between memory read and refresh cycle that we are going to discuss. Memory address to be refreshed is provided by the refresh mechanism counter and not by the microprocessor, right? So this memory address of the cell which is to be refreshed, that is provided by a separate thing which is called as refresh counter. It does not comes from this microprocessor's control bus or something, right? More than one memory chip may be enabled at time to save time. So when an externally interfaced RAM is there or DRAM is there, then you can activate several memory chips at the same time, and you can refresh them concurrently. You should not refresh them sequentially. They should be parallelly refreshed, right, to save time. The data enable control is disabled for selected memory chips. So if you have selected 2 or 3 memory chips for refreshing, then in that case, you should disable their data enable control, because if all of them will have their data controls enabled, your data bus will have data from multiple memory chips which is coming to that. So that is a situation which it would be able to handle. So the data enable control should be disabled, right? Then memory refresh is an independent and regular activity. So this is an independent activity, and this kills time of the processor. There is separate hardware which is dedicated for refreshing the DRAM, and it refreshes the complete DRAM, and the frequency of that is typically of the order of 10 to the power of 3. So 10 to the power of 3, that means in 1 second it will have refreshment 1000 times or its multiples, right? So that is the amount of activity that is needed to keep that memory in active state with all the correct values. So that will obviously kill the time of processor, and it is carried by refresh mechanism. So with these points in mind, let us now move to this thing, which is dynamic RAM interfacing. So I'm not going to elaborate on this complete diagram. You can see that there are several chips of dynamic RAM which are kept there, 16K cross 1, 16K cross 1. So there are 16K locations of 1 bit each, right? So this is just for illustration purposes. They can be of different sizes. And you see here that address lines, etc. have been connected from the microprocessor through this 7-bit mux. This is very important. These are the lines which will come from microprocessor, and these are the lines which will come from refresh and add counter. So, if the microprocessor wants to access these memory locations, it will be providing certain addresses through this, and through this multiplexer, those locations will be accessed. But if it is not using that, this memory needs to be refreshed completely, and that is why this AR0 to AR6, that is refresh lines from refresh counters, will be supplied through this multiplexer to select and refresh these chips. And you can see that there is a refresh timer and address decoding logic for which memories are to be selected for refreshing. So again, I have not covered this dynamic RAM interfacing in great details. You should only know that it consumes more amount of time and dedicated hardware to be able to refresh. But because of its advantages that we have seen, we still use this dynamic RAM. Right. So, I guess I haven't been able to cover this input-output interfacing in this lecture. I will definitely cover that in the next lecture. So, this is it for this particular video lecture, and I will definitely see you in the next video where we will start from this DRAM. Where we will start from interfacing of input-output ports, and then we will proceed further. So, thank you very much for watching this video. I will see you in the next one.